Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the short conference. Surrogate Programming and Primal Dual Surrogate Algorithm. PDS, Primal Dual Surrogate Algorithm for Nonlinear Programming was devised by Jesús Velásquez-Bermúdez in 1974, at the age of 22, and was implemented in 1980. In 1986 PDS was awarded with the Alberto Leon Betancourt Prize in Operations Research, by the Colombian Society of Electrical Calculation and Operational Research, ACCIO, award. The Colombian Association of Systems Engineers, ACCIO and ACCIO were integrated under a single association, ACCIO. At the age of 25, in 1978, Dr. Velásquez-Bermúdez founded, together with 3 other partners, Computerized Projects and Designs, abbreviated PDC Engineering. To start operations, PDC invested $400,000 in a ModComp Classic 7870 mini-computer to solve complex math problems. As part of the implementation, PDS was integrated as a cutting plane system for linear programming, and mixed linear programming solvers, PDC Primal Dual. The main optimization algorithm made at PDC was PDC Primal Dual. A bounded Primal Dual simplex algorithm, with multi-pricing, base inverse in product form, and handling the functional matrix in compact constraint blocks. Pivot and complement heuristic to accelerate MIP problems. Bender's partitioning and decomposition algorithm, using a variation of the standard Primal Dual method, to handle Bender's cuts as a dense matrix. Primal Dual Surrogate Cutting Planes, and Compact Matrix Generation. By then, the PDC Primal Dual could have been competitive at the level of the current Cplex or Gurobi. Surrogate Mathematical Programming. In 1970, Harvey Greenberg and William Pierscala wrote the seminal paper, Surrogate Mathematical Programming. The first work in this area was showed by Glover, 1965, who uses surrogates constraints to solve binary optimization problems. Afterwards, works of Ballas, 1969, Shafrian, 1967, and again Glover, 1968, are found. They present the uses of surrogate constraints to the same problem. Greenberg and Pierscala developed the basis of a general theory for surrogate programming which may be classified as a Lagrangian method. One of the first works in this area is the model called Generalized Lagrange Multiplier, GLM, developed by Everett, 1963. This method solved a general nonlinear problem by a sequence of unconstrained problems using the Lagrange multipliers. One of the difficulties to use this methodology is the existence of gaps for multipliers that solve the original problem. Greenberg and Pierscala, 1970, show that the gap problem in the case of surrogate programming is less restrictive than the surrogate GLM model. They suggest that the solution of a nonlinear problem may be obtained by a problem with only one surrogate constraint. Primal Dual Surrogate Algorithm, Theory, and Demonstration. There are 2 problems to be aware of in the PDS algorithm. The original problem that we will call P, which has a system of vectorial constraints in the form of inequality, gx less than or equal to vector b. The second, the surrogate that we will call S of lambda, which is a derivation of the original. Lambda corresponds to the Lagrange multipliers of the constraints of the original problem, so S is a function of lambda. S has a single constraint that is constructed from a weighted sum of the original constraints times their Lagrange multipliers. The objective function, fx, and the vector function gx are assumed to have continuous partial derivatives. The vectors L and U are limits that are part of the original constraints. The vector of Lagrange multipliers is non-negative. The constraint of S is obtained by replacing the set of M constrictions of P with a linear combination of them. When lambda is equal to the Lagrange multipliers of P, the problem S, with a single constraint, solves the problem P that is M constraints. The idea is to design an algorithm that, when solved, solves P. The following is the operation of multipliers, which appear as the basis for active restrictions. To do this, let's consider a linear feasible zone, bounded by 6 constraints. Associated with each constraint is an associated multiplier, as shown in the image. If 2 constraints are triggered, for the linear case the solution will be at an extreme point where the 2 constraints intersect. The value of the Lagrange multipliers of the 2 constraints will be different from 0. In this case, it is assumed to be equal to 0.5. For all other restrictions they will be equal to 0. The most complicated case arises when the problem is degenerate. In this case there are several solutions for Lagrange multipliers. In 2 dimensions, if the solution triggers only one constraint, all solutions will be in a convex set, and there will be only one non-zero multiplier. Another alternative is that the solution is at an extreme point of the convex set, and the Lagrange multipliers associated with the extreme point will be activated. The number of active Lagrange multipliers is limited and can therefore be removed from the constraint base. It acts as a column generation scheme. The following definitions are important in the PDS algorithm. Problem L minimizing z of lambda subject to the feasible space of Lagrange multipliers. The definition of the z gradient of lambda. Using the theory developed, it is possible to make an algorithm to solve the problem P through the problem S of lambda. The problem L is the dual surrogate of P, and optimizes over lambda vector that in the optimum is proportional to the Lagrange multiplier of the problem P. The evaluation of z of lambda implies the solution of S of lambda, for a given lambda, and we call it the primal surrogate. We have 2 questions about how to solve P through SL. 1. Is there an optimal lambda that resolves P? 2. If the answer is affirmative, how can we get it? When lambda is equal to the Lagrange multipliers of P, the problem S, with a single constraint, solves the problem P that is M constraints. The idea is to design an algorithm that, when S is solved, solves P. PDS works in 2 levels. First, in a dual surrogate level, PDS moves the dual variables lambda to minimize z of lambda. Second, in a primal surrogate level, PDS moves the primal variable x, to solve S of lambda, and evaluate the gradient of z of lambda. Those interested in learning more about the theory and demonstrations of the PDS, can review the draft. Chapter 28c, Subrogate Programming and Primal Dual Surrogate Algorithm. Next, we analyze the geometric behavior of the PDS. Suppose a concave objective function, whose isolines are represented by red lines. Suppose a minimization problem, whose objective function has the optimal without constraints on the black point, A. The feasibility zone is linear unlike the one previously analyzed. Visually, the constrained optimum can be defined as the one located in the blue dot. Assuming the unrestricted optimum as the starting point, the PDS trajectory must join point A with point Z. The next step is a lambda shift, depending on the direction of its gradient. This lambda motion brings x closer to the frontier of P. In this case this is the final step since it produces a feasible point in x. In the end, there is only one active restriction, the number 2. It's important to note that there are a set of constraints that aren't part of optimization, and that could be ignored from the start. Controlled experiments. This section presents 9 controlled experiments that show the theory presented previously. The detailed experiments are presented in the reference document. Each experiment is presented without a voice in 2 seconds. Case, economic load dispatch including transmission losses. For convergence testing and demonstration purposes, the PDS algorithm was implemented in GAMS. To do this, was used problem of the economic load dispatch including transmission losses model, corresponding to an NLP problem that is part of the model library offered by GAMS. The test GAMS code can be requested from HI. A professional version of the PDS algorithm may be provided by HI. This version can be used to solve large real problems. The GAMS program uses in the first phase, Primal, the CONUP algorithm to solve the nonlinear problems. In the second phase, Dual, it uses the maximum descent method based on the subgradient of the surrogate objective function. The following figure presents the results obtained for the case presented by GAMS. It can be seen that in iteration 4 the gap in the target cost has been closed. Two versions of the model were implemented, one NLP and one MINLP. Implementations in algorithms. Since its inception in 1980, the PDC been used in several algorithms. Its first use was as part of the PDC Primal Dual algorithm, in 1980. Mainly as cut shots for MIP problems. Since 1990, with the first version of OpTex, PDS was incorporated, to compact the database into a multi-level Bender's algorithm, and surrogate programming is currently critical in the management of the hippocampus and hypothalamus of the artificial brains that HI is investigating.